Hello again, this is Carson Meredith. In this lesson we're going to talk about the recent history of high-throughput materials development. In particular, we're going to cover the years 2000 to the current year. So I just want to review briefly what we covered last time. In particular, we talked about parallel catalyst screening in the 1920s as one of the very early developments in multiple samples in an experiment. In 1970, Hanna formalized this multiple sample concept. In 1990s, we saw the development of parallel spatially addressable libraries such as peptides, with 1,000 samples per library. In 1995, the important development of spatially addressable libraries of superconductors with 10,000 samples. And then this continued to be applied to other elements like polymers, phosphors, acylation catalysts, and LEDs. So this is actually an interesting plot of the number of papers published in peer-reviewed journals versus year, going from 1990 up to 2014. So these are all journal articles that involve the words high-throughput materials or combinatorial materials, including materials like polymers and metals and inorganic phosphors and things like this. But you see in 1990, you can't even see that there were maybe 2 or 3 papers involving these search terms. And by year 2000, there were over 350. And last year, there were over 1,000 papers published in this field. So you can see that really there's been an explosion of interest in this area over the last 25 years. So I'd like to pick just a handful of these that have occurred in the last 15 years and talk about them. And the first one I'll talk about is an example from my own work. In the year 2000, I was working as a postdoc at the National Institute of Standards and Technology in the polymers division there. And I worked with several people, Paul Smith, Alangir Karim, and Eric Amos. We applied high-throughput screening to a polymer physical property for the first time. The property we looked at was wetting. So when you have coatings and films, one of the things that's important is, does the coating actually remain stable on the substrate it's intended to cover, or does it break up into tiny droplets? So we actually made libraries that contained gradients, gradients in thickness in one direction, and gradients in temperature in the other direction. These are the 2 variables that affect polymer wetting quite a lot. And in one experiment, we were able to, even though these were continuous gradients, they represent something like 2,000 distinct combinations of thickness and temperature. And we were able to look on these libraries and rediscover or recreate a lot of the knowledge that had already been learned about polymer wetting in the decades before, really in one experiment. So we also continued this work looking at other polymer type properties such as blending. So many commercial polymers are actually not single components, but they're blends of multiple polymers. One of the important questions you want to know in blending polymers is, do they mix well? Are they miscible or immiscible? And to what extent are they immiscible? So we developed a way to blend 2 polymers by making composition gradients. So we had to use some different techniques than were already available for metal, which is the co-sputtering I talked about before, because polymers are processed usually in the solution phase or the melt phase. So we developed a way to do this, and we developed libraries that look like this, where you have a composition gradient along the horizontal axis. This is a blend of 2 polymers, polystyrene and polyvinyl methyl ether. You can actually also see there's an orthogonal gradient in the processing temperature. So this is a parallel 2-dimensional library with continuous gradients. And you can look at the bottom dark part, that's the 1-phase region where they mix well, and the top lighter part, where the 2-phase region where they don't mix well. So this allows you to look at hundreds of temperature composition combinations in one experiment. So there were other important developments in polymeric biomaterials in the 2000s. Joachim Kohn and his co-workers in his group at Rutgers University looked at biodegradable polycarbonates and other types of polymers. They actually created libraries of up to 10,000 polymer compositions, and they use these to select targets for biomedical applications. And one of the important ones that was developed was the first degradable radio-opaque stent for coronary artery disease. So other areas where high-throughput methods were applied include catalysts. So I'm including a result from the Meyer group in Germany for production of hydrogen fuel from methanol. So Meyer actually screened libraries with large numbers of catalysts. Catalysts were binary combinations or ternary three-component combinations of up to 29 different elements. These catalysts were converted to metal oxides, put into vials, and they developed a custom screening apparatus where they could look at 100 catalysts at once, exposing it to light. So this was a photocatalytic reaction where the exposure to light caused hydrogen to be produced. They used high-throughput gas chromatography to screen the production of hydrogen, and they could create diagrams like this one, where you look at the amount of hydrogen produced in combinations of three elements. So they discovered a new catalyst. It was a combination of aluminum, bismuth, and oxide that produced hydrogen at a very high rate. So that concludes the few examples that I want to talk about out of thousands that really exist. So what's next? What's next is I'm going to go over a brief overview of the types of high-throughput strategies that people use to screen through compositions, processing, structure, and properties, and I look forward to seeing you then. Thank you.